Let's learn about DeepSeek's DeepGEMM FP8 matrix multiplication. How DeepSeek and all of the other companies like OpenAI, DeepMind train large language models in FP8, floating point 8 precision, 2 times faster than classic FP16 or BF16. DeepGEMM is a just-in-time compiled high-performance CUDA library for FP8 matrix multiplication. So it's runtime just-in-time compilation system. Here's how it works. The Python entry point init.py exposes functions like FP8 gem not transposed transposed and not transposed not transposed. So it takes these two matrices and they can be in these two formats. You can transpose them before you send them to this or without transposing them, and it will be transposed inside of this function. When you are multiplying two matrices, so you need to transpose one. Then C++ dispatch, which is C++ API layer. This is what it looks like. Here on the side, I will scroll through the code, it's C++. This file, gem.hpp, is the main logical entry point. Functions like FP8 gem non-transposed transposed validate inputs and dispatch to kernel implementations. So we have that function implemented here. It's gonna first check if inputs are correct, and then it will call or dispatch to these kernels that are very fast implementations of matrix multiplication in FP8 using CUDA code. We will learn more about that, but let's see. Number 3, just-in-time compilation engine. So this is this entire folder. And runtime code generation and caching system compiles optimized CUDA kernels on demand. So this C++ function that I showed you, FP8 gem not transposed transposed, is the main piece of code of this entire repository. First, we have this shape must be mk times nk dot transposed. So when we transpose this nk, then it will be kn. So actually, the shape must be mk at kn. In the input validation in the beginning, it validates the shapes, of course, and ensures FP8 data types and proper memory layouts. Let's look at this first input parameter. So we have two separate tensors. So it will be, the first one will be saved as a.first. So if we say a.first, this is the actual FP8 matrix data, the numbers of the matrix values. Data type is FP, so floating point 8 with exponent for mantissa 3. Shape is denoted as mk. We will use this later. Each element is 8 bits, 1 byte. So if m is 1024 dimensions or nk is 512 dimensions, then in total there is half a megabyte in this matrix. Second element, a second, the scaling factor. The scaling factors, there is multiple. So because FP8 has limited range, this to represent numbers. These are maximum and minimum numbers that can be represented in this E4M3 format, and not every number in between them can be represented. So we're gonna take our BF16 or FP32 that can represent big numbers like millions and stuff and scale it into this range. Or we will take small numbers and scale it into this range, but we need the scaling factor to scale them back up or back down after this computation. Scaling factors vector can have different shapes. For example, it can be a number of scaling factors. So each row of this first matrix is scaled separately and has its own scaling factor. Then we have the same thing just broadcasted. So each of the scaling factors is in its brackets, its own dimension, its own mini array. So we have array of arrays, but each array is one scaling factor, so just one element. It's just broadcasted so we can later maybe multiply it easier with this matrix. Then we can also have one scaling factor for entire matrix, but this is less optimal because some numbers might be huge, some numbers might be very small. So if you have a small scaling factor to cover small numbers, then these huge numbers will explode. So usually you want to have more adaptive, because huge numbers will then get clipped and then information is lost. And vice versa, if scaling factor is big, scaling big numbers, then if you have very small numbers that get scaled down even more, then those small numbers will become zero or get clipped. So scaling each row separately here is a better option, less risky, and even if there is some clipping, it just happens in that row. Here, data type for scaling factors is float 32 or int 32. This is good, this is correct, this is a good way to keep scaling factor. I've seen some places keep it at 16, but 32 is maybe even better. So true value is FP8 value times scaling factor. If FP8 value is 100 and scaling factor 0.01, then true value is 1. Then we have this parameter b, which is the same thing. The first is FP8 matrix, second is scaling factor. Although I'm pretty sure there are some rules to apply to this second one, but I'm not sure, we'll see later. Then the third one is output matrix. So purpose, where the result will be written. Shape is mn. That's the shape of our output matrix. When we multiply mk, matrix multiply kn, we get mn. We will actually store this result in higher memory. So FP16 or 32. So this memory layout, this must be column major. So first column is stored in memory and it's stored like this. And then the second column here, the third column here. So we go column, 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 storing like these elements. Pre-allocated user must create this tensor before calling the function. So we have also parameter c, which is optional accumulation matrix. So it's optional here, and then it's just a tensor or a matrix. Purpose enables d equals a at b transposed plus c, instead of not having this plus. So it's like a bias in neural networks. It can also be used as residual connections, not just bias. Fused operations for performance, so if we have some random plus as well, we can also use this. So when it's present, it must have shape mn, same as the result of the matrix multiplication. Must be in 32 bits for numerical precision. Must have n or column major layout like D, like the result. So remember, torch column k float is a 32-bit data type float, and kb float 16 is 16-bit. We also have this k float 8 underscore e4m3fn, which is the FP8 data format that I was explaining. Then we have this fifth parameter, recipe. Its purpose is to control how GPU kernel is configured. So block M is how many rows processed per thread block. For example, 128. So we take 128 rows, and then how many columns? We can take 128 columns per one thread. So in this one thread in GPU, we take this chunk, 128 times 128. And this parameter, I'm not sure what it is. Num stages, pipeline stages for memory compute overlap, example 3. So this is example how it works. If num stages is 1, no overlap, it's first loading data, then computing, then loading next data. Number of stages 2, double buffering, while stage 0 is being used for computation. Stage 1 is already prefetching the next data tile. So the first data tile, for example, 128 times 128. Next tile will be same dimensions but next to it. When compute finishes, the new tile is ready. Classic trick to hide memory latency. Number of stages 3, triple buffering. The way I understand it, as the first tile is being computed, the second tile is already either loading into the computation or traveling through memory and waiting to be loaded, and the third stage or third tile is also being loaded and waiting after the second one. So this can dramatically affect performance, 2 times speed up possible with right choice. Then we have this compiled DIMMs. Purpose: tells just-in-time compiler which dimensions to optimize at compile time. Common values nk, optimize for n and k dimensions, most common. mk, mnk, so this would optimize for all. It will compile slower but faster to run. Or no compile time optimization, fast compile, slow run. So if you are testing, you use this to test fast. But if you are going with the big pre-training or training, then you use this. So the big thing runs faster. How it works: compiler generates specialized code for specific dimension sizes, trade-off, compilation time versus runtime performance. The more you wait to compile, the faster it will run when it's compiled. So this depends on if you are testing quickly and iterating or having the big training run. We also have this optimization flag, disable UE8M0 cast. So it's actually enabled. So we enable this format exponent 8 mantissa 0 for better performance on SM100. So is this just H200 GPU? I think this is all of the Hopper GPUs. I'm not sure. So if we disable it, we will use standard E4M3 format. Only relevant for H200 GPUs. Okay. Wait, it seems like this is just a scaling factor, so it's not a replacement for E4M3. You will not run a matrix multiplication in this exponent 8 mantissa 0. Instead, this E4M3 is used for actual tensor math, and this exponent 8 is used just for scaling internally in the GPU. Then we have memory layout detection. So if it's row major or column major. Row major, as I said, means each row is stored in memory next to row. And column is like, this is first column, second column, column. It's flattened in by columns. So you can see here, first element, and then same row, second element, same row, third element. But here, first element, but this is going down. This is the second element in the column. So column is same, but row is now, it's going down. So that's how it's stored. And if it's stored in row major, it's easier and faster to pick row by row, because you pick this row from memory and then next to it is the whole row. But if it's stored in row major and you try to pick the first column, you need to go from here, jump there to get the first element of each row to form a column. So that's slower. So you want to store it in either row major or column major, depending on what you need, if you need rows or you need columns. So this function that checks the major type is going to take in a tensor, and it will use striding. So you see here, if it's row major and you're picking a row, you need to just stride by one to get the whole row. But if you're trying to pick the column from row major, you need to stride by entire length of the row to pick the column. So wrong layout, if you're picking columns from a row major layout, you can get 10x slower memory access. So DeepSeek wants to optimize for that. So pick rows from row major or columns from column major. So we want both major in A and major in B matrix to be this K, which is the inner dimension. Whatever it is, it's second dimension here, first dimension here. So it's easier to pick this K, because those are getting multiplied. So we need to pick K numbers and K numbers here, and then pick K numbers. So we want them next to each other. Then we just got more dimension validations and type checks. I think I'm gonna end this video here. Next time we will learn more. You can check other videos on my channel, and see you next time.